Real experimental XAFS data can be messy and have systematic differences from ideal XAFS spectra, or at least have differences from other spectra that you might want to analyze. Correcting these differences makes it easier and more robust to analyze and compare multiple XAFS spectra. Hi, I'm Matt Neufeld, and this is part of the video series for using Larch for XAFS analysis. The XAFS Viewer application has a few dialogues for helping you do some of the most common kinds of corrections to XAFS data, and in this video we'll go over those. I should say that there is one sort of commonly needed correction that is not currently covered by the XAFS Viewer application, and that is applying dead time corrections to fluorescence data measured with multi-element solid-state detectors that do pulse processing. These are commonly used detectors, but there isn't a uniform way to express the dead time corrections in a way that can be easily imported and used by a GUI form. So if you were collecting fluorescence XAFS data with a solid-state detector, talk to your beamline scientists or about how to do the dead time corrections well before reading them into XAFS Viewer, or contact me or have your beamline scientist contact me, and we'll see if we can come up with a correction script for your data before reading it into XAFS Viewer. I'll come back to this point a little bit later too. For now, let's start with some of the most commonly needed correction types and show how to do that. The first is doing energy calibration so that data collected at multiple beamlines can be compared well, even though the energy calibration between them might be slightly different. So here I'm going to read in a few different metal foil spectra that were collected at different times and even different beamlines. And I'll read in a few of these. I'll read them in sort of one at a time. Again, I'm using energy and using minus log of the transmission chamber channel over I0. If this is new or seems unusual to you, there are other videos showing some of this. So I've read in a few spectra for a few different foils, and then there's a set here where I, from a different beamline and measured with a slightly different energy range. And I'll read these in. So if I select all of these and plot them together, especially if I plot them over the narrow range here, you can see that they're all pretty much the same. This one with a shorter energy range, I should just go tweak its edge step normalization so that they better compare. There's a previous video on showing how to do this in more detail. For now, this will do. Those match pretty well, but if I look in detail at the energy shifts, comparing the data from these there is a slight energy shift between them. If I look at the numbers here, they range from 7111, that one looks the same, but that one's off by 0.3 eV, which isn't a huge amount. You'll often see variations that are much bigger than this, but I also know that if I read in the data, what you might want to do is read in these other oxide data, which I should have read in order. These go well with this iron metal room temperature 1 spectra. So I'll move this one to the bottom of the list, and then I'll read in that one again. The Fe203 and the Fe304 data. These all went together. Were all measured at the same time. If I take this one and move it to the bottom, then I'll read in some of these other data that are labeled as H1 that were all measured at the same time on a different beamline. And you can see they also have a shorter energy range, but now if I plot these different metal foils together, there is a slight variation in energy. And so if we wanted to use these 3 metal oxides and compare them to these different phases, we would want to make sure the energies are calibrated. So to calibrate the energy, we will go to the data menu and then the recalibrate energy. The corrections I will show you all come from this data menu. So recalibrating the energy brings up this dialog. If I say I want to do the energy calibration for H1 iron foil, and I can say I could either calibrate that and apply a constant energy shift here, or I can say auto align to another spectra. So I'll auto align it to iron metal foil. That shows here the original and the shifted, and those two now line up very well. It's hard to see that they're different. They are. Those are different spectra, but they align very well. So I could save this as a new group, say H1 foil energy shift. I'll do that right now. I'll just save that as a group, and then I can reproduce this plot here by saying iron foil and taking those three spectra and plotting them together. Not this one, the one above it. Taking those three and plotting those together, and now the original iron foil is slightly shifted, but the other two are well within the noise of being on top of each other. But what I would really want to do is then take all of these other spectra that were measured at the same time and apply that same shift of 0.2 eV to those. So in fact, I'll go here and take this shifted one and select none and take this one and remove that from the list, and take all of these and select all below. So all of those H1 sets of data are now selected, and now I can say apply this shift of 0.2 eV effectively to all of the data sets, and that will overwrite those sets of data. It will shift the energy for all of those. Apply that, and now all of these are aligned together. They all have the same energy alignment, and if I select this one and the one we aligned to and plot those together, then those are still really well calibrated to one another, and the energy shift is is very close to each other. The energy in the alignment is very close. If I plot those two as derivative, you'll see how close they really are in that range. So those match very well. So that's how you do energy alignment from one spectra to the next. It's not uncommon for the energy calibrations to be different by more than this range, but 0.2 EV at the iron edge can be a significant shift in energy if you're trying to calibrate and do Zane's analysis, as we'll get to in a few videos. So for now, I'm going to get rid of all of these spectra and go on to the remove selected groups, just get rid of all of those, and go on to the next form of, and the next most important form of data correction, and that is to remove glitches from data. So here's data that's got a little bit of glitches in it, and I'll show you those. This is data that was measured in fluorescence. So when this comes up, I've measured the last data, read in the last data set as transmission, so it remembered that. I want to make sure that log is not selected, and I want to take the sum of iron K alpha spectra. So here there's sum of iron K alpha. That's all of the spectra from the different MCAs in this data set together. This data set had 7 different MCAs and a few different ways of measuring them, including the dead time correction factors, but this channel has all of that combined. So I'll read those in and show the full energy range. And you can see that there's some glitches out here in this range. The glitches aren't too bad, but we should get rid of those. So the way we would, and I should also say we should also do the normalization a little better between here and here. That looks better. But let's get rid of these. Let's try to get rid of these glitches in the spectrum. So to do that, again, the data menu to deglitch data. That brings up this dialog. We select which of the data sets, which of the groups we want to work with. And now we can select a single energy or a range. So I'll zoom in here, and let's say I want to remove this point. So I click close to there and then select the pin here to use the last selected point from the plot. That's 74.57. If I remove that point and now show this, you can see that that's removed that point. It hasn't tried to interpolate, it just removed that point. And we might want to remove some other ones. So if I say that point, now let's remove that one as well. And again, I'm clicking on the plot near close to the point, and then clicking on the pin to select that point. You could type in an energy if you want. You might also look at this data set and say, you know, we should just remove all of the data in this range. It looks like there's a couple of glitches. This is not uncommon for them to come in groups of 2 or 3 and to have both a positive and a negative spike in them. So here we can select an energy range. We could select above so that if we wanted to, say, select all of the data here and remove it. So I could just say, let's take this point and say, all of the data above this value, let's just remove all of that. And now the data set has no data above 7682. But also, I think we want to remove that data in the glitch region, and to do that, we can, again, I'm just zooming in, and we can say between 2 energy points. So I'll say this point here as the low end, and then this point up here as the high end, and say, let's remove all the points in between there. And you can see those are gone, and it hasn't filled them in with other data sets, it's just removed them. And so now I can either save this as a new group, I'll do that, that's iron biotite A, and 1_clean. You could give it a different name if you want. I'll just go with the default, and we'll say we're done here. Now if I select those 2 and plot them, you can see that the data has been both truncated and those points removed. So that's how you deglitch data. Moving on to the next kind of correction you may want to apply, that is to, I'll select those and get rid of those. The next sort of correction you may want to apply is to rebin data, especially data collected in quick XAFS mode at particular beamlines where they slew the monochromator at constant rate and use a time signal to collect data. They can collect thousands or tens of thousands of energy points, but you really want to be able to combine those together to increase the statistical accuracy of the energy points. But also in the downstream processing for extended XAFS data, we're going to merge and rebin the data anyway. So we might as well do that here. So to do that, I'm going to show a few different things with this one data set. Palladium oxide collected in quick XAFS mode at constant angular rate from a Spring 8 beamline. So here when I read this data set in, actually this data was collected in angle. If I go here and show this, here it didn't collect the energy in EV, but it collected in angle, and so we'll want to convert that to energy. In fact, you can also see that the array names are a little hard to understand. So first I'm going to edit the array names, which brings up this dialog box. And you can see here that I'm pretty sure that the first column is angle drive, so the requested energy, and the second one is angle read. And then it looks like the next one is a constant of 0.045, and I believe, I'm gonna guess that that's the count time. And then the next channel is I0 and the next one I1. So I'm just gonna say apply those changes. We could also say use column numbers to just give column 1, 2, 3, 4, 5. For now, let's just do this. I think these are right for this data set. And now we can tell this that the angle is not in units of EV, but in units of degrees. And that we'll try to convert that then, and it will also select that this is XAFS data. It treats raw data from other file formats. You can read that in, but it doesn't then apply any of the normal XAFS treatments to the data. So we can read that in, and now if I say I1 over I0 and minus log, that actually looks like XAFS data. It looks correct, but it's not Palladium XAFS data because the Palladium edge is more like 24 keV, and that's because this is assumed so far that the mono despacing was 3.13 is appropriate for silicon 111, but in fact this used, we can read it here, which is really nice. This used 1.637 for silicon 311. So if we go select that, paste that in 1.637 and hit return, then that will show that the energy is around 24 keV, which is correct. And now we are able to read this data in correctly. And it even says, warning, the XAFS data may need to be rebinned. So I'm gonna click OK, and this brings up a dialog box that says this data set may need to be rebinned. Rebin now, and I will say yes. You could say no and then read it, do that correction by bringing up the data Rebin Data dialog from the data menu there. So here, this data set, it's identified a value for E0 that seems reasonable, and in the pre-edge range, it'll go from -30. I'll make this be a little wider for maybe 30 is okay. -30, is it minus? Something like that, and maybe make that slightly finer. It collected a lot of data, so we should let it use a lot of data, and then it'll take 2 EV steps in the pre-edge range, and then 0.25 EV steps in the Zane's range. For Palladium K-edge, that's fine enough resolution. And then in the extended XF range, it will go out to the end of the data, 18 keV, in steps of 0.05 inverse angstroms. So stepping out constant in wave number, not in energy. So I'll save that as a new group just to show that data, but you could just overwrite it too. Save that as a new data set, and we're done here. We've now, but it turned out that the pre-edge ranges were not very appropriate, so we're going to just select those again and plot that normalized XAFS data. In fact, I'll just show again for this a better job at doing the edge step normalization. And look, the polynomial range was incorrect here, so we will make sure that we've selected that well so that it does a better job of normalizing that XAFS data. In fact, maybe if I make that auto, I think it'll set it back to quadratic. And that looks appropriate. And now if I show that as normalized XAFS data, that looks pretty good. We could go to the XAFS tab and look at that XAFS data in KiFK, but we'll get to that in a later video. So that's rebinning the data collected, especially in quick XAFS mode, or collected at much too fine a scale to really be useful. So I'm going to go on to the next correction type, and that is to do over-absorption corrections. So again, for data collected in fluorescence mode, especially with a solid state detector, but even with a ion chamber or any kind of detector, if the element of interest is too high of a concentration, then the data can be suppressed and needs to be corrected. Again, this is fluorescence mode, and it's in units of energy and EV. So I'm going to select the right arrays to read in. So that's the iron K alpha sum and dead time corrected for this data set, which is this data set has a little bit of dead time correction as well, a little bit of dead time, and so that's corrected in that channel. And now if I plot this group, this looks pretty good actually, but in fact this isn't terribly overabsorbed, but it's slightly overabsorbed, and that is that the fluorescence coming out is absorbed, is attenuated by the sample itself, and so that leads to the shortening of the absorption depth as the energy changes. So here we can make a correction for that by correct overabsorption. And to do this, you'll need to know, for a reasonable approximation of the stoichiometry of the sample, I'm going to say that this is Fe to SiO4. And it'll do the correction, and it doesn't need to be super accurate in the stoichiometry. In fact, we often find when doing this that this approach overemphasizes the correction. So if I turn that down so that it's more like Fe half SiO4, as if there was less iron, then this is the correction that's done. So the overabsorption will suppress all of the values of mu so that the oscillations are smaller, and so that especially the white line is greatly suppressed. So this uses the flow program algorithm from Daniel Haskell et al. There are other algorithms that can be used for doing dead time or for doing over-absorption corrections. The flow algorithm seems to be the most appropriate for Zane's data, where these corrections are the most important. For XAFS data, they will give a systematic error in the Debye-Waller factors that you analyze. And so if you're doing extended XAFS analysis and want the Debye-Waller factors to be accurate, then you'll need to make sure that these corrections are done. There are actually other algorithms available. If you're interested in having those be readily available within Larch, contact me and we can easily add those, I believe. May want your assistance in that. But for Zane's, this is the generally considered the better approach to use the flow algorithm. And again, we could do the correction, we can play with the stoichiometry, so that's with a half of, if the stoichiometry was really low, if I said that was 10% iron, I do the correction is very small. And if I say that it's stoichiometry of 1, it's bigger as the iron, the absorbing element becomes more of the mass of the sample. The correction becomes larger. So if I say this, and I'll save that as iron silicate for FeSiO4. That's not actually the right stoichiometry for this data set, but it's close enough for this application. And again, those are the two. What's important about that is that you can see that while the edge step is pretty good, it actually moved the relative energies of the main edge as the correction is much larger as the absorption goes up. It also then, relative to the edge step, made the pre-edge peaks larger in total. It didn't really move the pre-edge peaks in much detail, but a little bit. So doing any analysis on fluorescence data where the absorbing element is a major component of the sample, stoichiometry can be important to do these kind of corrections, at least to first order. Okay, so moving on, we have one more kind of correction or one more sort of processing that you can do with data. I'm going to show you one last semi-correction that you can do, and that is, I'm going to read in data from an Athena project file. Here I have some Athena project file with some data for data collected in Herfd as well as transmission XAFS on europium. So I'm going to select. So here, when I read in an Athena project file, you can select which of those data sets to read in, and I have two standards, a 2+ and a 3+ standard measured in transmission and in Herfd at the same time, and then a sample for low concentration europium in a class. So I'll just import all of those spectra. And one of the questions for Herfd data always is, so there's the 2+, and here are the 3+ spectra together for measured in transmission in Herfd. And then this other data set, I'm going to show this here in purple. Clearly, you can see that the data on the unknown on the low concentration sample is 3+. That makes it really easy to work with. But one question that often comes up when dealing with Herfd is whether you could just smooth the data, the Herfd data, to reproduce the transmission data, the total fluorescent yield data, or if you can take data measured in standard mode and just do a deconvolution of it to reproduce the Herfd data. So let's try that. From this data menu, there is a dialog to smooth data. So let's take this very messy data set for a glass for an unknown, and there's a couple of different smoothing methods. One is to use a boxcar average to smooth the data. I can increase then this to 10, and that will smooth the data a bit. So let's try that. Let's call this, I'll call this smooth 10. I'm just going to save that. And now if we plot those two together, that's the data and the smooth data. And in fact, you can see it didn't do much to, except for just make it cleaner. So that's a boxcar average. That's pretty good. There is another method for smoothing data, the Savitsky-Golay method, which uses both of these n and order parameters. This method actually, strictly speaking, requires that the data be evenly spaced in energy. You can apply it anyway and hope for the best. And we often find that it works out reasonably well. So here I can say that that's Savitsky-Golay smoothed with those parameters, and I can save that as a new data set. Now if I plot those together, all three of them, and the differences between those two are pretty minor, and which one did the better job of smoothing you can argue about all you want. But, so as we smooth that data, did it make it appear to be more like the europium oxide data, is really the question that we would want to answer. And the answer is, it appears to still have a much stronger white line. So this europium data was measured in Herfd, so that's fluorescence, and on a standard, so it was, there is the potential for being self-absorbed, but that's the data for transmission. So that data you would consider to be correct transmission data. So can we smooth it even more, or can we convolve it with a Lorentzian to make it broader? So if we make that a Lorentzian broadening of 2, return, and then save that as, now that's looking like, I'll call that Lorentz lower 2 EV, save that. Does this look more like our transmission XAFS data? And we're getting, you'll see that we're getting close, but not quite. Maybe we need to increase that deconvolution even more. Let's try that. That's now Lorentzian 3. I'll save that. And look at those two together. That's getting, again, close, but still not perfect. So you can continue doing that, and you can see that we've sort of over-broadened the raw data that we've broadened it so that it's actually wider in width of the main peak than the transmission data. So we sort of over-broadened it with convolving it with a Lorentzian of 3 EV. We can also go the other way. So we can take the transmission data here and ask if we can deconvolve that to make it sharper. So if you have fine enough data, you can say take a Lorentzian and sharpen the data by deconvolving it with a Lorentzian, say of 1 EV. I'll make that just for the sake of simplicity, say I'll deconvolve that with a Lorentzian with 1 EV and save that as a new group. And does that better reproduce the Herfd data? Select none, plot that with the Herfd data we have, and you'll see that that's still too broad, so I need to deconvolve it more than that. So at 2 EV, that looks now more sharp. So I'm going to save that, plot those together, and you can see that now that's looking like that's still too broad, but also, if I continue, 2.5, save that, still too broad, and we're not reproducing the main peak correctly, and it looks like we're introducing a shift. In fact, if I make that even bigger, let's just go all the way to 4. You can see that the Deconvolve data now has a much sharper dip past the edge, which is, we're going to see is not correct. Plot those two together. This is just to say that now we're reproducing the intensity of the white line, but we've missed something here. And I think this is I think this is showing that while you can smooth and deconvolve data, that Herfd is somewhat different than simply deconvolving the transmission or the fluorescence data. So I think I've gone in enough depth for the kinds of corrections you might be able to apply to data and what else you can do. I should say, but it's a final word, there's one more to do. And that is adding and subtracting spectra. I showed that you could take groups of data and merge selected groups. That's a fine way to add data together. But you sometimes may want to take two data sets and subtract them, or do something else with them, like do a weighted average. So in this dialog, you can bring in multiple spectra and label them as just A, B, and C, and create new spectra based on those values. So you could say A minus 10 times B and calculate that. That obviously is not producing a very good or useful spectrum, but you can do a more robust you have more freedom in how you then apply those additions and subtractions of different data sets. So you can take differences of data if that's what you want to do, or subtract off 90% of some other data set. A minus 90% of B, and so on. So you can do those sorts of analyses. I think for now that's enough of the corrections, and we'll if you have comments or questions about these corrections or what else can be applied, feel free to contact me or leave comments below, and we'll see you next time. I hope that was helpful for getting your data corrected and able to be analyzed. And we'll see you in the next video. Thanks.